Hello dear students, welcome back to NEET World. So in this session, we'll be continuing our discussion on mesomeric effect applications. Okay, so in the last sessions, I have explained inductive effect and its applications, and I have also given some questions from EAPCET previous year papers. Right now, I hope you watched that session and you have used it very effectively for your preparation, right? So in this session, we will be discussing mesomeric effect more clearly with the proper PYQ questions, okay? Right, let me show you. First of all, let me give you some complete clarity on mesomeric effect from previous discussion so that we can attempt the questions without having any confusions, right? So let me show you some questions. I mean, before going to that questions, let us discuss the concept of mesomeric effect. See, there are two effects, there are two types of mesomeric effects. One is plus M effect and minus M effect. So when we can say plus M effect and minus M effect, students, it is very easy. See, to the conjugated system, see, mesomeric effect is observed only in conjugated system. What do we mean by conjugation? See, pi bonds, sigma bond, again pi bond, like they should be positioned at alternate way. See, for example, I am writing benzene ring here, right? So now see how the pi bonds are located here. They are at pi, sigma, pi. So it means they are at alternate position now. So this is what conjugative positions we can say. Now this will shift over here and the pi bond from here will be shifting here, like that. Conjugation will be taking place. Delocalization of pi electron is taking place. Now to this type of conjugated systems, now I am inserting a group G here. So now what happens when we insert a group G, which is electron releasing group? Okay, so let me show you here. Pi electrons in this way and lone pair electrons here. The lone pair electrons of this electron releasing group will be participating in the conjugation with this pi electron. See, lone pair, sigma bond, pi bond. So they are at conjugative position now. So these lone pairs will be donated into the ring. So when it is donated into the ring, then the negative charge will be generated on this ortho position carbon of this phenyl ring, of this benzene ring. See, now it will be like G, positive charge on G and negative charge on this ortho position carbon, like this. Again this negative charge donated into the ring, and now pi electrons will be shifted onto the para position. Therefore what you are going to get here, again see here what you are going to get. You are going to get a negative charge here and G plus here, like that. So what you are seeing on this benzene ring, you are getting a negative charge. When this will be seen? When we have a electron releasing group. If the G is electron releasing group. See, what can be the electron releasing group? See, here I have mentioned this many examples to be an electron releasing group. That means it is activating the ring by creating more electron density, that is negative charges at ortho position and at para position. So what type of groups these are? All these are, see, all of them are having a common thing, that is electrons here, lone pair electrons, non-bonding electrons here. See, this is one set of non-bonding, again here also, like this. Non-bonding electrons are there, therefore we can say them as electron releasing group, and the effect known as plus M effect. See, it is a ring activated now, so ring activating groups we can say. So where they are activating the ring? At ortho positions, at this para position. See, again if you conjugate this pi negative charge over here, negative charge will be seen on this adjacent ortho position, like this. Okay, so these are the scenarios you have seen when you have written this many conjugative sites. Now if you see, the negative charge is creating at ortho positions and para position only. There is no negative or positive charge at this third position, that is at meta position. It means mesomeric effect will not be operated at a meta position. Okay, it will be activates at ortho and para positions, operates at ortho para but not at meta. Remember this one simple important point here first of all. Okay, and let me show you with the electron withdrawing groups also. See, if there is electron withdrawing group, let us see, I am writing here aldehyde, which is an electron withdrawing group. So now what it will do? See, there is no non-bonding electrons on carbon to donate into the ring now. So now what happens in this case is, which is more electronegative between this carbon and oxygen? We know oxygen. So that creates a positive charge on the central carbon here, I mean carbonyl carbon group. Okay, so now when it is positive charge, to stabilize this positively charged carbon, the pi electrons of the ring is shifting towards a positively charged carbon. Therefore, this positive charge carbon will be stabilized. So what will be the scenario now here? So you are going to get something like this, CO minus H. This pi bond is shifting here, so double bond here, a positive charge here, like this. Okay, so like this you are going to get. Now after forming these, at ortho position, what is the charge you are seeing? Negative, but here it is negative, but here it is positive. So whenever there is electron withdrawing group, what I am saying, whenever there is electron withdrawing group, that will drag the that will withdraw the electron from the conjugative system, that is from the ring, conjugative ring, like this. Okay, so now what happens, a positive charge is created on this ortho position of this benzene ring. Okay, now once again you can shift these pi electrons to the positively charged carbon, O minus H. See, if it is shifting here, you are going to get a positive charge on this para position carbon, right? Again, after this, you can shift these pi electrons from there to here. We'll get pi bond here, positive charge here, CHO minus, like this. So now what are the charges you are seeing? You are seeing a positive charge at ortho position, para position, again at ortho position, but there is no positive charge generated at meta position. So from this again you can say mesomeric effect, whether it might be minus MA effect, plus MA effect. The effect will be observed only at ortho and para positions, not at meta position. Okay, right. If it is electron releasing group, ring will get activated and will get a negative charge at ortho and para position. If it is electron withdrawing group, it will withdraw electrons from the ring and generate a positive charge at ortho and para positions. Okay, remember these two statements to answer the questions. Okay, right. Now what are the electron withdrawing groups? It is very important to be identify whether the given group is electron releasing group or electron withdrawing group. Then only you can able to get whether it's a ring activating or ring deactivating. Whenever we have minus M effect, like electron withdrawing groups, that will deactivate the ring by withdrawing electrons from the ring. Okay, whenever you have plus M effect, that is electron releasing group, that will activate the ring by donating electrons into the ring. Okay, so now what is the main thing? Identifying them. See, whenever on the benzene ring, on the conjugative system, if we have a group G, if any non-bonding electrons are there, most generally it will be electron releasing group. What I am saying? Most generally it is electron releasing group that will activate the ring. Okay, so but instead having in this manner, so if it is something like this, some G is there, there is no non-bonding electron, this G, and G is having a pi bond with the other G, some other element. So this is one element, this is another element, like X, Y you can see. Okay, I am generalizing to identify that. What is the standard way? See, there is X atom, X is attached to the Y. Okay, there is no non-bonding electrons on X. Now what happens? So now this X, between X and Y, the pi bond will be shifted towards Y. Now what is the charge created on that X atom? Positive charge. So now what happens? From the ring only it is withdrawing the electrons. So we can say there is no non-bond electrons on this directly attached atom of the phenyl and adjacent atom. Between them we have a pi bond. So shifting of bond takes place out of this ring and creates positive charge within this phenyl ring. Okay, so any of this group here which I have mentioned can act as electron withdrawing group, that is minus M group or minus M effect we can say. Okay, so these are the things. Now what we can conclude, whenever there is electron withdrawing group, that will create positive charge in the ring, okay, in the conjugative system. Okay, right. Now what are the effects we can, what are the applications we can get out of this? See, these are the applications. We can able to give the stability of reactive intermediates. What are the reactive intermediates we have? What are the reactive intermediates we have? Something like carbocations, carbon anions, and next carbocations, carbon anions, free radicals. This stability we can explain using the mesomeric effect. The next, acidic strength of carboxylic acids, phenols, and basic strength of amines. like acidic strength of organic acids we can explain, and basic strength of organic bases we can explain using mesomeric effect. Okay, this is second application. And third application here we have is bond length. We can also explain the bond length, how it is varying the given compounds due to this mesomeric effect. Okay, this is third application. And fourth application is reactivity of organic compounds. So which organic compound is more reactive, less reactive? Okay, like example they will ask, out of which of the following four options will be more readily react in SN1 reaction or SN2 reaction. So for this you can use our application of mesomeric effect or inductive effect or hyperconjugation to decide the reactivity in a particular reaction given. Okay, right. These are the things to be remembered here. Let me explain this using some questions, then you will get more clarity. Yeah, let me explain this and let me check whether everything is clear. So which organic compound is it? Yes. Yeah, so here look at this. First application is I am giving with respect to this phenol, acidic nature of phenols. How can you decide acidic nature of phenols here? So which is more acidic, they will ask. How can we answer this? Very easy to answer. See, whenever there is electron withdrawing group, what happens? Withdrawing groups withdraw the electrons from the ring. Right now that will withdraw electrons from the ring. So when it is withdrawing electrons, see here acidic nature, it means what? See, if HA is an acid, then it releases H plus ion, forms A minus and H plus. See, organic acids are weak acids. If they are weak acids, we'll get an equilibrium state like this. See, if the conjugate base formed after releasing H plus ion is more stable, then equilibrium moves forward, then I can say this is more acidic, this HA is more acidic. So acidic nature of carboxylic acids or organic acids depends upon stability of this conjugate base. Okay, so now just look at this phenol. So after releasing H plus ion, this phenol after releasing H plus ion, what will be the scenario? So after releasing that H plus ion, we will get a phenoxide ion, O minus, NO2 and H plus. Okay, this is what the phenoxide ion right now. So now this phenoxide ion will be stabilized by the conjugation of this negative charge into the ring right now. So now it will be stabilizes more effectively, this negative charge will be dragged more effectively inside the ring towards this nitro group side when it is electron withdrawing group. So if this attached group is electron withdrawing group at para or ortho position, organic acids acidic nature increases. Okay, so here we have electron withdrawing group and these two are electron releasing groups. CH3 and OCH3 are electron releasing groups. Now what they will do? They will release the electrons into the system. They already have negative charge after removing H plus ion. Okay, so now already if there is negative charge, that should be dragged from that oxygen atom towards into the ring. But these groups are pushing more electron density towards that negatively charged oxygen. So it means more electron density on an atom or species, that will be less stabilized. So simply you can remember electron withdrawing groups increases acidic nature. Okay, acidic nature. So where do we have here? Option 2 is having electron withdrawing group, no? Therefore that will be more acidic comparatively with the remaining options. And after this they are asking about order. So after this OCH3 having lone pair electrons, no? So it will shows mesomeric effect. So mesomeric effect with releasing nature. So if it is releasing, then its acidic nature is very less right now. So 4 is least. After this here we have methyl group and here chlorine. So chlorine is having lone pairs, but due to its more electronegativity, it will be having more dominating minus I effect than M effect. In case of halogens only, inductive effect will be more dominating than this mesomeric effect. Okay, therefore I can say 2, then next 5, and after this between 1 and 2, 3, these are releasing groups, there is no groups. Releasing groups means acidic nature decreases, no group is relatively more acidic than having releasing group, and highly acidic is electron withdrawing group. So I can say 2, 5, 1, then next between these two things, this is weakly activating, this is more strongly activating. So I can say 3 here and least one is 4. This is how you can answer the question. Okay, right. Let me give you few more examples. So these are the compounds you need to remember: sulfonic acid, carboxylic acid, phenol. These are given. Which is more acidic? They will ask. See, sulfonic acid is more acidic because you just look at the structure of sulfonic acid. This is the structure of sulfonic acid. Now if we release the H plus ion, you will get a negative charge on this oxygen. So now it can be participating in a conjugation like this. Whenever it is in conjugation like this, more the number of conjugations, more is its acidic nature. See, and conjugation is between 2 oxygen atoms, and between these 2 oxygen atoms only. Whenever conjugation is between the same atoms, we can call it as equivalent conjugation. If it is equivalent conjugation, it will be more effective than normal conjugation, like between heteroatoms conjugation. We can consider equivalent conjugation is more effective. Now look at here, carboxylic acid, RCOOH. Okay, after releasing this H plus from this carboxylic acid, you will get O minus. So now here also you have conjugation. This is between oxygen with this oxygen one time, and this side. There are 2 sides we have conjugations. Here only one side. So more the number of conjugation, more is the acidic nature. So sulfonic acid is more acidic than this carboxylic acid. Okay, remember this. When we compare with phenol, carboxylic acids are more acidic. Compare with alcohols, phenols are more acidic. Again, all alcohols are less acidic than water except methanol, you can remember. All alcohols are less acidic except methanol when we compare with the water. Okay, remember this statement to answer the questions. Very, very important statement. Alcohols are more acidic than alkynes. Alkynes are more acidic than ammonia and methane. Okay, that's it. Just remember this order. Next. Here, look at this, X and Y compounds are mentioned. See, just tell me what is the bond length here. How it will be varies, like these 2 things are there. What is the bond length here? X, and here it is Y. So whether X is greater than Y or Y is greater than X. So how can you answer? See, the lone pair electrons of nitrogen of this amine will be in conjugation in both cases. Okay, like this, and these are in conjugation. This is in conjugation with the oxygen pi bond of this aldehyde group. Here it is with nitrogen. We know minus M effect of nitrogen is more when we compare with this aldehyde. So which is more minus M effect here, more electron withdrawing nature is for nitro group, that will withdraws electrons more effectively, and this these non-bonding electrons are more effectively dragged towards this nitro group side and making it to be nitrogen carbon positive charge, I mean double bond, more effectively in this case when I compare with this. Why? Because nitro group is more effective minus M effect, like stronger minus M effect showing more stronger electron withdrawing group showing group, which one? Nitro group. Therefore it will drag that lone pair electrons more effectively and creates a double bond here when I compare with this. Therefore here more double bond character, na, more double bond character, more bond order, less bond length. So what happens? More double bond, so less bond length. So Y is having more double bond character, so bond length will be less when I compare with X. So you can say X is greater than Y. Okay, so this is the way to answer the question. Okay, that's it. Next, like example they will ask. Next, look at this, plus M effect increases the basic nature of amines. So how can you answer this? See, I have mentioned here methylamine and this normal aromatic amines, aniline with electron releasing group, and like this I have mentioned, and here aniline with electron releasing group, and this is simple aniline. Okay, now look at these options, very easy to understand. We know this nitrogen of this aliphatic amine is donated to a H plus ion, that is what Lewis basic nature we are saying. So Lewis basic nature for aliphatic amines are more than aromatic amines, because these lone pair electrons of aromatic amines are in conjugation. So if they are in conjugation, they have very less ability to accept this H plus ion, whereas in aliphatic amine, nitrogen lone pairs are freely sitting on the nitrogen atom only, that will be easily accepting this H plus ion. So I can say aliphatic amines are more basic than aromatic amines all the time. Okay, now between the aromatic amines only if we want to discuss, see the lone pairs electrons here, like this we have. See here I am writing electron releasing group containing amine, electron releasing group containing aromatic amine, no group here, and here we are writing NH2 lone pairs, and here electron withdrawing group. Now in this case just tell me which is more basic. So which is more basic, electron releasing group, electron withdrawing group, and no group. How can we identify here? Very easy, look at this. See basic nature means nothing but tendency to accept a H plus ion. Where do we have more tendency to accept H plus ion? See, whenever there is electron releasing group, that will also release electrons into the system. Okay, if these electrons are releasing into the system, that will be given towards this nitrogen atom now, therefore that will pushes this nitrogen atoms to accept H plus ion more easily, therefore electron releasing group containing amines, aromatic amines are more basic. So first one is more basic, then the normal aniline, and here we have electron withdrawing group. What it will do? It will withdraw the electrons of nitrogen of this aniline towards itself, therefore these are less available to accept this H plus ion. If they are less available to accept H plus ion, I can say this is less basic, this is less basic. So this is a final order of basic strength of aromatic amines. Now tell me answer for this one question, so that I can consider that you are clear with the concept. NH2 and here CH3. So tell me ABC which is more basic, out of this ABC which is more basic. Yeah, tell me which is more basic out of these three options. Yes, so what is the nature of methyl group here? It is a weak ring activating, okay, like electron releasing group here, and this is nitro group strong ring deactivating. This is electron withdrawing group that will withdraws electrons of nitrogen of amine towards itself, towards this nitro group side, therefore these are very less available, so it is a least basic. Okay, here electron releasing group that will activate the ring and also enhances the basic nature of amine to accept this H place, so that electron releasing containing amines are more basic. So 1, 2, 3 A, B, C will be your answer for the question. Okay, right. Next one, what is the use? Again, carbocation stability, carbon anion stability, free radical stability can also be explained. See, electron deficient, which are electron deficient of carbocations and free radicals are having only 6 and 7 electrons. It means both of them are electron deficient. Both of them are electron deficient. So if these are electron deficient, so if any electron releasing group or plus M group is attached, then the stability of carbocations and free radicals will be enhanced. Whereas electron withdrawing groups are present, if electron withdrawing groups are present, then stability of carbocations and free radicals will be decreased. For example, look at this. I am writing electron releasing group something like OH, and here I am writing CH2 plus, and this one is CH2, and here NO2. Now what happens to the stability of these carbocations? Very easy. See, carbocations means how many electrons are there with the carbon? Only 6 electrons are there. If there is only 6 electrons, these are electron deficient. Now carbocations are electron deficient. Now if they are deficient, if there is any group that will donate electrons into the ring which stabilizes this carbocation, right now. So if these electrons are given into the ring, that will be moves towards that, electrons will be shared with this electron deficient carbon, and it will be now stabilizes, because electron density on this carbocation will be increased in now 6 become like 7 or 8 like that. So it should be now 6 only, carbocation is 6 only, but it must be increased to 8, means it requires electrons. Okay, if it is requiring electrons, there must be an electron releasing group attached. Okay, so if electron releasing group is attached, carbocation stability increases. So electron releasing groups or plus M groups will increases carbocation stability, Now here we do not have any groups, but here you have electron withdrawing group. Nitro group is electron withdrawing group now. So what is the structure it has? Just look at this nitro. How can you write this? Double bond O and O minus, like this you can write with a day 2 bond. Now what happens here? This pi bond of oxygen will be shifted onto the oxygen side. Okay, that creates a positive charge on the nitrogen, and pi electrons of this phenyl ring is shifting towards nitrogen. Now what is charge created in this benzene ring? No, you are getting a positive charge. Okay, if it is shifting here, you are going to get a positive charge. See, what is this? Positive charge and positive charge. See, both carbons are now becoming more electron deficient. If the system is more electron deficient, that will be least stable. Right now it is highly unstable. Therefore electron withdrawing groups, minus M groups, decreases stability of carbocations. This is one more example. Let me show you some questions related to this stability of carbocations and carbon anions. Okay, so that you will feel that yes, there are some questions asked on this. Okay, so now what is there here? So we have electron withdrawing group. Just tell me what will be your answer for this question. So I am writing here a conjugative system. Okay, to this here I am writing CH2 plus. This is option A. You just tell me stability of these carbocations, and option B here CH2 plus, and this side I am adding NO2. Option C CH2 plus, double bond here, and here I am writing OCH3. Now tell me which is more stable carbocation out of these three. Out of these three carbocations, which is more stable and why? Second option or third option or first option or stability order you can see. See here carbocations are there now. Carbocations are electron deficient. What they are? Deficient. Now it requires electrons from the other atoms. Okay. So if it is shifting here, you will get a positive charge here. Again this will also be in conjugation, shifts like this. Here, yes, this is stabilizing. Yes, this is also stabilizing. But what type of group here we have? Nitro is electron withdrawing group. So whatever the positive charge shift generated here, that will be destabilized by this nitro group. But in this case, oxygen is having lone pairs. So now if it is shifting here, we will get a positive charge on this carbon, that will be stabilized by the pi electrons again. Now if it is shifting here, you get a positive charge. Now this positive charge is stabilized by lone pair electrons of oxygen. So where carbocation is more stabilizing? Third option. So C is more stabilized, and here this positive charge is destabilized by nitro group, but there is no such, so it means which is more stable? C. After that A, and least stability is for B, that's it. So this is a question, this type of question asked in previously in JEE main. Okay, right. Next. So next, similar to this, we need to discuss about another intermediate, that is carbon anion. What is that? Carbon anion. So for example, I am writing like this, CH2 minus again nitro group, and here OCH3 only, same previous question only with a different groups here, with a different one, that is carbocation, here it is carbon anion. Now tell me which is more stable and why and how? So carbon anion means carbon with a negative charge. Negative charge means more electron density on the carbons now. If it is more electron density, what type of groups we required? See, if more electron density, see a person is having more weight on his head, now how he feels? More strained now. So there will be more electronic repulsions in this small carbon size, like due to small size electron repulsions are more. So now there is a group needed which drags the negative charged electrons towards itself. If this conjugated system is dragging electrons towards itself from this carbon anion, the carbon anion stability increases. So now dragging means electron withdrawing group is required to stabilization of carbon anions. For carbocations we require electron releasing groups. For carbon anions we require electron withdrawing groups for their stabilization purpose. Now tell me here what type of group we have here? Nitro group. What is the nature of nitro group? Withdrawing. See, it will withdraw the pi electrons towards oxygen, creates a positive charge on nitrogen. Now this will be shifted here. Okay, we will get a positive charge here, and this will be shifted here, you will get a positive charge here, to that positive this oxygen negative charge is given. So this kind of conjugation is seen in this case. But here if you observe, already negative charge, and this oxygen is donating its lone pair. So I can say this is electron releasing group or plus M group. So if there is electron releasing group, will it be stabilized? No. Why it will not be stabilized? Now it is creating a negative charge toward nearby the carbon by electron conjugation. Okay, like this conjugation. So negative charges are generated here. So it will be repulsive interactions right now. So whenever there is carbon anions are there, you just need electron releasing electron withdrawing groups for their stability. Carbon anions are stabilized by electron withdrawing groups. So here we have withdrawing, here releasing. and there is no group. It means which is more stable? Withdrawing. So B. After that, no group is more stable than having releasing group. Right now, because releasing group releases electrons and destabilizes it more. Here no such group. So it will be intermediate. Okay. Now I will give you one more question on this. Just answer me. Out of these 4, writing here nitro group, I am writing here aldehyde group, I am writing here CH3 group. Tell me which is more stabilized? Carbon anion, or stability order of this carbon anions. Which is more stable carbon anion out of these 4 options? Huh? B. I want order of the stability of these 4 carbon anions. B is more stable. Why B is more stable?
Because nitrogen is a withdrawing.
Nitro group, not nitrogen, nitro group is electron withdrawing. Minus M group. What is it? Minus M, as well as minus I also. Okay. What about this aldehyde? CHO means, write the structure. C double bond OH. See, these pi electrons taken towards oxygen creates positive charge. So now this carbon takes electrons from the ring. So what is this group? Aldehyde also electron withdrawing. So both of them are electron withdrawing groups. It means both cases carbon anion is more stabilized because of electron withdrawing group. But which is my more stronger electron withdrawing group? Nitro group. Therefore more stabilization is in B. After that C. And what type of group here it is attached? CH3. So we can say this is electron releasing group. What is it? It is a releasing group. So if it is releasing group, that will be less stabilized, like it can be destabilized actually. So I can say least stability is for D. So here A. That's it. Is this clear? Next. Next we have hyperconjugation. We will study this hyperconjugation. Once after finishing this, I will show you the most generalized PYQs of EAPCET and NEET from these 3 effects. Okay. And here first one, hyperconjugation means how can you understand? See, just take a carbocation. To this carbocation, adjacent carbons are there now. These are called alpha carbons. What I am saying? Alpha carbons. Now, carbocations contains how many electrons? 6 electrons only. So 6 electrons only means electron deficient or rich? Deficient. Okay. So now what it requires? These carbons required electrons. So that electrons are given from adjacent alpha hydrogens. See, these hydrogens are there now. The adjacent carbon of this this carbocation is called alpha carbon. If this is alpha carbon, hydrogens are called alpha hydrogen. So now how it will be shifting? It will be donating sigma CH bond electrons to the carbon. So the delocalization of alpha CH sigma bond electrons into the vacant p orbital of this carbocation is called hyperconjugation. What is hyperconjugation? The delocalization of sigma CH electrons into the vacant p orbital of carbocation is called hyperconjugation. See, delocalization of alpha CH sigma electrons with vacant p orbital or pi star orbital of alkenes is called hyperconjugation. So this is the effect, this is the application of carbocation stabilization using hyperconjugation. So now what happens here? If this between carbon you will get a double bond, and this will remains as it is, and this hydrogen will get a positive charge. Like that, how many alpha hydrogens are there? A, B, C, 3 are there now. So it will repeats with all these 3 hydrogens. So it means the number of hyperconjugative structures will be equals to number of alpha hydrogens present on the given compound. Okay, so more the number of hyperconjugations, more is the stability. So more the number of resonating structures, more is the stability of carbocation. Now tell me, out of these 3 compounds, just tell me here which is more stable carbocation. So tell me, it's very easy. Yes, you can easily answer this. Tell me, which is more stable carbocation out of this A, B, C, D? D. Why D?
Because CH3 3 are there.
How many alpha hydrogens are there in the fourth case?
9.
See, this one is 3, 3, 3. Total 9 alpha hydrogens are there. So 9 times it can be stabilized by hyperconjugations. Here also how many are there? 6. Here 3. Here 0. So where do we have more number of alpha hydrogens? So this will be the order of carbocation stability. So that's why we are saying finally, as carbocation stability order means what you will be saying, 3 degree, 2 degree, 1 degree, and least is methyl carbocation. Okay, so what are the effects explaining the stability of carbocations here? One is hyperconjugation, other one is inductive. So inductive means what is the nature of alkyl groups? That is a plus I effect. Okay, it is not for like alkyl carbocations, stability is explained only by hyperconjugation and inductive, not by mesomeric effect, because there is no conjugation, there is no pi electrons in conjugation now, therefore no mesomeric effect is operated here. Okay, right. Next, let me give some more questions here. So which carbocation is more stable? Tell me out of these 3. Which is more stable? So what is the degree of this carbocation? See. So 1 side, 2 side, 3 side. So 3 degree. And what about this? Secondary. Now tell me the order. This is primary. So which carbocation is more stable? So it means it's B, A, C. That's it. This is the answer for the question. Okay. Now I will show you some EAPCET questions here. Just tell me your answers for that. Tell me the stability of carbocations from the 5 options. 4 options. Which is more stable carbocation? How can you answer this? Tell me. Write their structures first. C6H5 means it is a phenyl ring attached to CH. This is benzyl carbocation. Second option it is vinyl carbocation. And third option it is 2 methyl groups are there, secondary carbocation. Right? This is secondary. And this one is primary carbocation. And this is normal sp carbon having positive charge. Okay, so now which is more stable carbocation out of this? See here you can have mesomeric effect with the pi electrons of this ring now, like this. So it means one is more stable because mesomeric effect is highly dominating effect. Next, after this you have alkyl groups. How many alpha hydrogens are there with respect to this carbon? 3 alpha hydrogens here, 3 here. So total 6 alpha hydrogens. If there is total 6 alpha hydrogens, 6 times hyperconjugations, and I can also say alkyl groups as plus IFX. How many are there? 2. Okay, so it means 1, after that 3, so 1, 3, and the fourth one is having 3 alpha hydrogens, and I can say 1 inductive plus I effect, okay, and 4, and between these two, this is sp carbon, this is sp2 carbon. So where do we have more electronegativity? Electronegativity is more, like more s character, more is the electronegativity. An electronegative atom should contain negative charge, not positive charge, but this is more electronegative having positive charge. It means which is least stable out of these two? 5. So I can say 2, 5. So where do we have this kind of option? 1, 3, 4, 2, 5, first option. Okay, that will be your answer for the question. Easy? Next. So you have studied application of what? Application of hyperconjugation. One application is over. Next one, application of hyperconjugation. First one is stability of carbocation. Next one is stability of carbon free radicals. Carbon free radicals. Stability of free radicals. What is that? Stability of free radicals. Okay. How it will be stabilized? Check here. Similar to carbocations. This is alpha to this radical carbon, the adjacent carbon is alpha. How many alpha hydrogens are there? 3. So now each time see this radical carbon contains how many electrons? Count now. 1, 2, 4, 6. 6, and this radical electron is 7th electron. Okay. So still how many electrons are required for this carbon to get octet configuration? 1 more. Okay. So that 1 electron comes from the weaker CH sigma bond, that is alpha CH sigma bond is breaks homolytically and pairs up like this, okay, and gives C, C, H, 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 H and H dot like this. How many times it will be stabilized in the same way? 1, 2, 3. How many alpha hydrogens are there with respect to this? 3 alpha hydrogens. So 3 hyperconjugations are possible. So 3 times it will be stabilized. I mean 3 resonating structures are possible. Likewise, more the number of resonating structures, more is the stability. Now you can take CH2 dot CH3 or CH3 CH CH3 again with dot here, CH3 C CH3 CH3 again and dot here. So tell me, out of these 3 options which is more stabilized? Third one. Why third one? Alpha, alpha, alpha. How many alpha hydrogens are there? 9 alpha hydrogens are there. So 9 times it will be stabilized by hyperconjugations. Okay, 9 hyperconjugations are possible, 9 resonating structures, and I can say this is plus I groups also. So how many plus I groups? 3 plus I groups. Like that you need to sum up all the effects possible to give the final stability of a given compound. Okay, so which is more stable out of this? C, B, A. Okay, and after this you just answer me this question. The correct order of stability of the given 4 radicals, which is more stable radical here? Which is more stable radical? D. Why? Like order I want. See, this is primary radical, not in conjugation with anything. Okay, it means primary radicals we know relatively less stable. Let us check. This is tertiary radical, we know tertiary radicals will be more stabilized when we compare with the primary. Okay, now here you can see what type of radical it is. This carbon radical attached to 2 carbons means it is a secondary. Okay, and what about this carbon attached to 3 carbons, it means it is a tertiary. Okay, so we have 2 tertiaries and 1 secondary, 1 primary. Now which is least stable? Definitely primary. So B is least stable, then secondary one is C, and after that we have these 2 options. Okay, so in these 2 options it is very easy to understand. Okay, see there is double bond now. So double bond means what it is? Is it in conjugation? Is it in conjugation with this radical? No, conjugation means they are alternate position, double bond, single bond, and a radical can be there. Like that it should be there, but is this in that way? Double bond, single bond, again single bond, then radical. So this is not a conjugative position, that is isolated position we can say. It means no conjugation, but this is sp2 carbon. More electronegativity now. More electronegativity means more minus I effect. More minus I effect means less stability for this carbon free radical. So between this 1 and A and D, which is more stable? A. So you can say A is more stable, after that D. Okay, is this clear? AD, CB. So AD, CB, option C. Perfect now? Right. This is the way you need to solve the question. You answer me for this. These are the given 4 carbocations. Tell me their stabilities. Very easy again, the decreasing order of stability for the given carbocations. What to do? First of all, identify type of carbocation. This is primary. It cannot have any stabilizing factors like mesomeric effect here. Only you can have one inductive effect like alkyl group, one inductive effect, one plus I effect, and one alpha hydrogen, like this you can write. And for this is a tertiary, so it can be stabilized from this side, this side, this side by hyperconjugations and inductive effect. Okay, so it means tertiary. This is secondary, and this is also secondary. Now we know which is more stable. Tertiary carbocation is more, so definitely B will be more stable. So after B, identify between A, C, D. Here these are 2 are secondaries. This is primary. So which is least stable? A. So keep it A least. So from this also you can conclude your options. B greater, A least, B greater, A least. So you can eliminate first 2 options. Next, between these 2, now between these 2, how can you identify? Just count alpha hydrogens. How many are there here? 1, 2. Here are 1, 2, 4 alpha hydrogens in total. Here 1, 2, 3. So where do we have more number of alpha hydrogens? More the number of alpha hydrogens, more hyperconjugation, more stability. So D is more stable than C. So BD, CA. So BD, CA, option C your answer. Again easy now? Right. Let us move forward with few more questions again. One more application of hyperconjugation is stability of alkenes. What is the third application? Stability of alkenes. See, I am writing alkene like this, CH2, CH2. This is alkene only, ethene. Now I am writing the same double bond carbons here, CH3 here, and hydrogen, 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 like this I am writing. Now if you see, the adjacent carbons are there now to this double bonded carbons. These are double bonded carbons. To them adjacent, to this adjacent means this one only now. So adjacent carbon is called alpha carbon. Hydrogens present on that is called alpha hydrogens. How many alpha hydrogens are there? 3 alpha hydrogens are there. So can I say these are alpha hydrogens? No, these are not alpha hydrogens. Only the carbon attached to the alkene carbons are called alpha carbon. Hydrogens present on that carbon is called alpha hydrogens. So 3 alpha hydrogens are there here. Okay, stabilizes the double bond. How it will be stabilizing? Just check here. See, this is pi bond now. So now the alpha hydrogens will be donated into the pi star orbital of this alkene carbon, and now making it negative charge. Like this it will be formed. See what is happening, this CH sigma bond of alpha carbon is shifting. So when it is shifting, already carbon is having 4 bonds. Now the pi bond is weaker bond, shift to the adjacent carbon, we will get a resonating structure like this. So we know more the number of resonance, more is the stability. How many alpha hydrogens are there here? 3 alpha hydrogens are there. So it can be stabilized by how many times? 3 times. Okay, like that, more the number of alpha hydrogens on a given alkene, more is the stability. For example, I am writing alkene like this, one more alkene like this. So tell me which is more stabilized? What to do here? First of all, these are 2 alkene carbons, adjacent carbons, these are alpha carbons. How many alpha hydrogens are there? 1, 2, 1, 2, and this one 1, I mean this is carbon, alpha carbon is this one, 1, 2, 2 this is alpha, this is also alpha, 1, 2, like that. Just identify number of alpha hydrogens. See in this case how many are there? To these carbons, alpha carbon is here, this one also and this one also. Just count number of alpha hydrogens maximum in which case? In this case. How many are there? 6 plus 4. So 10 alpha hydrogens, 10 hyperconjugations are possible here. Here how many are there? 2 this double bonded carbon, 3 plus 2, 5, and 2 this is alpha. Total how many are there? 7. And in this case 4. So where do we have more alpha hydrogens? More alpha hydrogens in third case. So more stability is for third alkene. So 3, 2, 1. That's it. This is your answer. So based on this understanding, tell me your answer for this particular question. Very easy, I know you will answer this. It is almost the question we have discussed, like 53. Option 1. So how it is 1? You are saying this is more stable, that is correct answer. Okay. So how it is stability of the following compounds based on hyperconjugation? See, double bond carbon here we have. 2 these adjacent carbons are these things. Identify how many alpha hydrogens? 3 plus 3, 6, 7, 8, 9, 10. So 10 alpha hydrogens here, and this one 3, 4, 5, 6, 7. 7 alpha hydrogens here, 1, 2, 3, 4. 4 alpha hydrogens here. To this only 1 alpha hydrogen. So where do we have least number of alpha hydrogens? First option. So therefore it will be least stable. So least stability is 1, 1. So you can eliminate these 2. Where do we have maximum alpha hydrogens? 4. 4 is highest stable. Yes, in both cases 4. After this is more 7. 7 is more stable, 7 alpha hydrogens, so more stable in 3, then 2. Then 2. So option 1 will be your perfect answer for the question. Okay, next. Answer me this question, again important. This is from NEET. Hyperconjugation occurred in which options hyperconjugation is possible? See, what is the primary criteria for hyperconjugation? Alpha hydrogen should be there. So to this free radical, check whether alpha hydrogens are present or not. If present, where? If not, no hyperconjugation, no stability. See, to this adjacent carbon is this one only now, so alpha. So do we have any alpha hydrogens on it? No. Alpha carbons are there, but hydrogens? No. This side you can see, this is carbon. 1, 2, 3, 4. 4 bonds are there. So do we have alpha? No alpha hydrogen, so no hyperconjugation in this case. In this case, do we have Phenyl is nothing but this ring only. So no hyperconjugation. And in this case, how it will be? How it will be? From this side you have one alpha hydrogen, right? Here also you can have one hydrogen, but this alpha hydrogen does not participate, but this one will participate this side, from downside, methyl group side. Okay? So because at bridge head you should not generate a double bond. So there is no hyperconjugation from above side, but from this below methyl group side we have hyperconjugation. How many are there here? 1. So in which compound it is possible? Only third option case. So only third option. How easy it is? Very easy now. Right. Next. Can you identify that? Hybridization of each carbon. Very easy question. CH3 means sp3, like CH3 and one more sigma, 4 bonds sigma, 4 sigma bonds sigma. This one is sp2, this one is sp3, this one C triple bond N. So how many sigma bonds? 1 and 2 sigma bonds. So sp. So where do we have? sp3, sp2, sp3, sp. First option. Okay. And 2 bonds NO and NO in CH3 NO2 are of same bond length due to, see, it's very simple. CH3 nitro group methyl nitromethane is given. They are saying why the bond length of oxygen is same here. What is the effect we can say? Yes. See what happens here? The negative charge of oxygen donated here, pi bond will be donated onto the other oxygen. So this is what equivalent conjugation now. Why I am saying equivalent conjugation? The conjugation is taking place between 2 same atoms. If it is between same atom, we can say equivalent conjugation. So due to this equivalent conjugation, we can say bond length is same. So which effect is that? Conjugation of pi electrons is nothing but resonating effect, resonance effect na 4th option. Okay, that's it. Next. So again very important ma, this is, tell me, which is more stable? The correct stability of following alkoxides. You are saying second option. Okay, why second option? Can you justify your answer? See, negative charge pi bond nitro group. Negative charges will be stabilized when there is electron withdrawing group. See, here we have electron withdrawing group and the conjugation is continuous from oxygen to nitro group. But in this case, see, this negative charge is in conjugation with this pi bond, not with the nitro group. And this pi bond is in conjugation with the nitro group also along with oxygen right now. So there is some kind of cross conjugation is there. This is a continuous conjugation, this is a little cross conjugation. But here there is no such conjugation only. Having conjugation is better than having no conjugation. So it means no conjugation means not stabilized much here. Okay. So not stabilized much means which is least stable? A. So A is least stable. Then next out of these two, B, and we know C is more stable because it is a continuous effective conjugation. So where do we have A, B, C? Second option. Okay. Right. Next. Can you answer me this in the same manner that we discussed in the last slide? See here how the conjugation is here. Carbocation. Carbocation requires which type of groups to be attached? Releasing group should be there. So what do we have here? Releasing group. Releases electrons into the ring like this. So stabilizes carbocation. So which is more stable here? 4. Between these three, answer is done. Between these three, see here you have conjugation like this. Okay, out of this 4 and 3 which is stable? Definitely 4. Between 2 and 3 if I ask, this will be donated here. Okay, after that you will get a positive charge here. This positive charge is stabilized by pi bond, okay, and this pi bond is in conjugation with lone pairs. These lone pairs are not in conjugation with this pi bond, okay, but it means what I can say, this is in cross conjugation. So cross conjugation makes it to be less stable when we compare with the continuous conjugation. So 3 is more stable than 2. Is this clear? And between these two things, like this only, okay, only some type of small conjugation is there, which is cross conjugation, again pi electrons and this negative lone pairs. So which is more stable out of this? 4, next 3, 2, 1. Okay, try to answer in this way. So whenever you are practicing now, maximum try to elaborate in a maximum extent. I mean, apply at your maximum level when you are solving the question, then you can improve a lot. Okay, simply solving which is more stable carbocation, we know fourth one, but along with that, what are the other ways to make it more clear with the concept? Try with every question whenever you are doing, okay, especially with PYQs. Tell me here, decreasing order of basicity of the following amines. The decreasing order of basicity of following amines is, which is more basic amine? What to do? Basic nature means take one H plus ion. Just imagine that this proton, basic nature means H plus ion you take, which of these 4 compounds abstract this proton very easily, that is more basic. So who will attack that proton? Just consider the lone pair electrons in each case, like this. Who will donate lone pairs to that easily? If that electrons are freely sitting on nitrogen, that will accept H plus easily. Here these lone pairs in the first case are in conjugation with the ring pi electrons. So aromatic amines are less basic compared to aliphatic. See, fourth option is not aromatic, it is aliphatic, no conjugation with the ring. Okay, therefore 3 is more basic. Okay, 3 is more basic. Now you need to compare 1 to 4. Between 1 to 4, the lone pair electrons of this pyrrole are in conjugation with the pi electrons of ring, that is responsible for aromatic nature. See, for aromatic nature, the lone pair electrons are in full conjugation. If they are in full conjugation, they are very less available to accept a proton. More in conjugation means less available to accept a proton. If they are less available, I can say it is least basic. So which is least basic? Fourth one. So third one is highly basic, I mean out of this 4 options, more basic, and fourth one is least basic. Now try to insert this 1 and 2 options here. See, where do we have this kind of options? 3 is more basic, 3 is more basic, and this one also, this one also. You can eliminate 2 options. And the next one here, I am saying this is in conjugation, this is not in conjugation, this is just easy to donate. So where do we have? First option. Okay, that's it. Next, this is not the question of discussion here. See, there are the effects, I can say there are 3 like electronic effects are of 2 types. Okay, temporary effect, permanent effect. So temporary effect and permanent effect. Permanent effect comes here for mesomeric effect, hyperconjugation, as well as inductive. Okay, and one more electromeric effect is there, that is temporary effect. What I am saying? Electromeric effect is temporary. Now read these statements. See, again there is some involvement of other topic also, just keep it aside. You might get confused with this 4th option and all. Okay, let me give you other questions. This is done? No. Tell me, what is the answer for this? Tell me, what is the answer for this? Very easy. Carbon anions are mentioned. Relative stability of carbon anions asked. So, see here which is more stable carbon anion here, see This is having C6H5 means phenyl rings now. How many are there? 2 phenyl rings are there. Negative charge. Negative charge stabilized by this side as well as this side. And here CH2, CH, CH2 minus. Again this is in conjugation. But this is only one type allylic carbon anion we have, which is in conjugation. But where do we have more number of conjugation? In 4 or in 2? 4. So it means which is more stable? 4. So where do we have 4 is more stable case? 4, 2. 4, 2. Only this option now. So remove all other. Option 3 is your perfect. If you want, you can compare between 1 and 2. See this sp carbon now. Yes. Sp carbon hold negative charge more effectively, or sp2 hold negatively charged more effective? Sp more electronegative, strongly binds the electrons. So that will be more stable. So 4, 2, 1, 3. That's it. Okay, right. Next. Can you try this question? Which of the following is most stable form of the given structure after rearrangement? So tell me how rearrangement takes place first. Option B. Yes, super. But there is no option for that. See, what are the things present on this carbon? All of them are methyl groups only now. If there is hydrogen, the migrating ability or migrating aptitude of hydrogen is more. See, actually what happening here, first of all, carbocation given is primary. Primary carbocations are least stable. So that will undergo rearrangement to form a more stable carbocation, either secondary or tertiary, depending upon availability. Now, all these methyl groups are attached to the carbon, central carbon. Now, there is only possible way is to shift a methyl group, then it converts into a tertiary carbocation. Right now, how it will be? See, if methyl group is shifted here, so we will get CH3, C, CH3, CH2, the next CH3, this positive charge. So do we have any carbocations like this? So if not, that might be a printing mistake, but option should be like that only. Okay, is this clear? Definitely this will be your answer for the question. Is this clear or not? Okay, shifting of this thing. Okay, this is a EAPCET 2020 question. Next. Tell me for this, lacks hyperconjugative stability from 4 options. Which one is lacking hyperconjugative stability? How can you answer this? See, what is the primary criteria for hyperconjugation? Alpha hydrogens. Carbocation is there, to that alpha carbons are there, and on that alpha hydrogens also there. So hyperconjugation is present. Here also alpha carbon, alpha hydrogen. Okay, here also you have alpha hydrogen. So A, B, C have hyperconjugative stability. But in C there is no alpha hydrogens, no hyperconjugation. So C. Okay, clear? Next. This is simple question. I hope you will answer me this, that from the following compounds, the one which contains both sp and sp2 hybridized carbons. Easy. I know you can able to answer that. Okay, you can try that. Next. This is also based on hybridization. You can easily answer. Now tell me for this. In which of the following hyperconjugation it is not possible? Very easy. Option? No. See, positive charge is there. This is positive charge. To that, alpha hydrogens are there or not? Yes, it can be possible. Okay. And in other options, if you observe, option A will be your answer for the question. How it will be? See, alkyl benzenes also stabilized by hyperconjugation. See, alkyl benzenes means this is benzene, one alkyl group, one carbon, some hydrogens, like this. See, to this double bond, adjacent carbon is there. This is what I can say? Alpha carbon only na, with respect to double bond. Hydrogens are there, alpha hydrogens only na. Yes. Similar to alkenes, our alkyl benzene also will be having hyperconjugation in this way. So that you will get. Like this, okay, this is happening or not, alpha hydrogen is shifting or not. So alkenes stabilized by hyperconjugations. So this is also an alkene now, unsaturated dienes are like triene is there, means this is also unsaturated. Alkene means, yes, if just check for the alpha hydrogens, yes, here you have alpha hydrogens or not with respect to double bond, yes, so hyperconjugation is there. So stability of alkyl benzenes also explained by hyperconjugation. More the alpha hydrogens, more the stability of that alkyl benzene. So here you have 2, yes, it is stabilized 2 times by hyperconjugation. Here you have one hyperconjugation takes place. But here if you see, to this carbon only methyls are attached. Do we have any alpha hydrogen, any hydrogen on this carbon itself? No. So no hyperconjugation in option A. Hope complete clarity you got on hyperconjugation applications. What are the 3 applications? Important applications are stability of carbocation, carbon anion, free radical. And one more thing, their bond length they will also ask. See, whenever there is a conjugation is taking place, like this we have. Now what happens during hyperconjugation? Sigma bond, single bond becoming a pi bond, double bond. So what happens to bond length? See, sigma bond, single bond becoming a pi bond means bond order increasing now. If bond order increases, bond length decreases. So they will ask application of this bond length also by giving different example questions. Okay, right. Okay. So you can see this question and you can answer me. Okay. And especially those who are in online, so just give me your answers for these questions in the chat box. Definitely I am going to look into it, even if it is wrong, no issues, I will be correcting it. Okay, and this one also you can answer me, and this one, all these questions are as homework, consider and answer me in the chat box. And this one also, just look into the questions or take a screenshot and try. Yeah, so these are the questions for the session. So thanks for watching. Stay connected with our NEET World channel. Thank you. ఏమో అట్లా వచ్చి అట్లనే కూర్చున్నావు.